In this example, we're going to do a hypothesis test to test a claim where we have two independent samples. So here we have a study where we want to investigate the fatality rate among patients who have serious injuries when they're transported by helicopter versus being transported by ground. So what we're going to do is we're going to test the claim that the fatality rate is actually higher for those patients transported by helicopter using a 0.01 significance level. So I'm going to highlight the claim. Oops, let me use my highlighter. The claim that we're going to do the test on. So here, the claim is that the rate of fatality is higher for patients transported by helicopter. And make a note to myself here that because we're dealing with rates of fatality, this is a reminder that we're dealing with a population proportion, which we call P. Okay, and P represents the fatality rate. And so we're looking at the fatality rate for two different populations. The first population is the group that is transported by helicopter. So I'll call P1 the fatality rate for the group transported by helicopter. And we want to compare that to P sub 2, which is the fatality rate for those transported by ground services. I'll just say ground, okay? All right, so I'm going to make a note to myself here that the original claim that we're testing is that the rate for the group by helicopter, so P sub 1, is higher, meaning greater than the fatality rate for those transported by ground services. So P1 greater than P2. Notice that this does not contain the equal sign. So that means that when we do the hypothesis test, I'll go ahead and write that down. The first step to our hypothesis test is to write down the hypotheses, the null and the alternative hypothesis. So again, because this original claim does not contain the equal sign, that's going to automatically become the alternative hypothesis. And I'm going to keep track here that this is the original claim. Okay. And then also because it has the greater than sign, I know that this is going to be a one-tail, right-tail test. Okay. All right, so that means that the null hypothesis is going to be the statement that P1 is equal to P2. So the null hypothesis always contains the equal sign. We always assume that the two fatality rates are the same until we have enough evidence to state otherwise. So off up in the top here, I'm going to write down all the sample data that I have to work with to do the hypothesis test. So for that first group, let's see here, the sample size was 61,909 patients. And then out of those patients, 7,813 of them died. That gives me a fatality rate, which we're calling P hat sub 1 of 7813 divided by 61909. I'm going to write this as a decimal. So that is a fatality rate of 0.126. And then for the second group, let me make the notation here. This is N sub 2, those transported by ground. Out of 161,566, X sub 2, 17,775 of them died. That gives us a fatality rate, which I'm calling P hat sub 2, of 17,775 divided by 161566, which gives me a fatality rate of 0.11. So let me just highlight this in red, my two sample proportions here, P hat 1 and P hat 2. So we can see with our eyes here that 0.126 is not the same as 0.11. So clearly there is a difference in the two fatality rates, but again, in statistics, we want to know if that difference is significant enough. Is it significant enough for us to reject the null hypothesis that says that there is no difference? So the only way to know is we have to calculate our test statistic for that difference. So the test statistic is going to be a z value for the difference between P hat 1 minus P hat 2. So I'm going to use the calculator for this. Again, on the calculator, you're going to use two proportion z tests because we have two independent samples. We're trying to test the difference between two proportions. We always estimate with the normal distribution, therefore we have the z. value, and then of course we're doing a hypothesis test. So when you put in all the relevant information, the calculator is going to give you the following corresponding test statistic, which is a z-score of 10.75. And then I'm going to go ahead and write down here the p-value that the calculator is going to give you when you use a two-proportion z-test. That p-value is, let me see here, the calculator gives you 2.93 e to the negative 27, but hopefully you guys have learned at this point that that is your calculator's way of writing a very, very small number. So basically this is 0.0000. So imagine that I have, you don't imagine, just write down there's going to be 26 zeros. So I'm not going to write all that down, but hopefully you guys can see it. That's basically zero. That probability is so small, we're going to just call it zero. Okay, so what does this look like on the bell-shaped curve? So recall that our significance level, alpha, is 0.01, and because this is a right tail test, 0.01, that entire area is going to be in the right side of this distribution. So I'm going to go ahead and label this distribution with 0 in the center. Remember that a value of 0 means that the difference between P1 and P2, right, is equal to 0, meaning that this is where P1 is the same as P2, okay? All right, so on the right tail, how do I know how much to shade? So how do I know how much represents a 0.01? To do this, I will need to find the critical value. So on the calculator, the critical value that corresponds to an area of 0.01 on the right, use inverse norm on your calculator, and inverse norm will give you a critical value of 2.33. So I'm going to go ahead and mark that. So 1, 2, 3 on the right hand side. I'm going to mark that in black here. So 2.33 is about right here. That's 2.33. That's your critical value. This critical value separates the critical region, which I'm about to shade in red here. So this right here is a critical region that has an area of 0.001. Okay. All right, so now we want to see if our test statistic, which I'll highlight in green here, I want to know if this lies in the critical region. So I hope you can see that 10.75 is much larger than 3. So I don't have enough space here, so this is not drawn to scale, but this is where I would mark my test statistic of 10.75, which is our test statistic. Our test statistic is the z-score that represents the difference between p hat 1 and p hat 2. So we can see here that our test statistic does fall in the critical region. So now if you're using the critical value method, we can make a conclusion about the null hypothesis. So here I would reject the null hypothesis. So that means I'm rejecting the statement that the fatality rate for the two groups is the same. In fact, the fact that our test statistic falls in the right tail actually implies that P1 is greater than P2. So I'm going to reject the null hypothesis. I know I'm going to reject it because using the critical value method, the test statistic, which is 10.75, falls in the critical region. And this again tells us that the difference that we see in our sample data, so the difference between p hat 1 and p hat 2, is significant enough for us to reject that the difference between P1 and P2 is 0. Okay. All right. Now, if you're using the p-value method, right, notice the p-value is very, very small. So I can barely highlight the p-value here on the right tail. So that's your p-value right there, which is basically 0 because it's so small. It's all the way at the very, very tip of the right tail. We see that the green shaded region that I just shaded in the right tail is much smaller than the red shaded region. So here we would make the same conclusion. You would reject the null hypothesis because the p-value, all right, is less than the significance level. Okay, so our p-value of 0 is less than 0.01, and so we can also reject the null hypothesis if you're using the p-value method. Okay, so how do we state the final conclusion? So here, because we reject the null hypothesis, right, that means that we don't have enough evidence to support that null hypothesis. We're going to reject it, right? And the original claim is the alternative claim. This means that our evidence is supporting the alternative, which is also the original claim. So here, you would state that there is sufficient evidence. So there is sufficient evidence to support the claim, which is the alternative hypothesis, to support the claim that fatality rate is higher for patients transported by helicopter. Okay. All right, so in the next video, I'll show you how to make a conclusion using an appropriate confidence interval.